talk, so I'd like to thank those of you with the stamina to actually still be here. And I thought maybe we should begin by thanking the organizers, and in particular Liam, who I hear did most of the work for this week. Okay, so in the next, I guess, 55 minutes, I wanted to try to give an idea about how to visualize foliations in three manifolds. And just a reminder, we have these assumptions. So M3 is compact. Let's for today just think about the boundary. Well, maybe it's empty, or maybe it's a union of tori. So it's compact, connected, oriented. When we care about smoothness, C infinity. And F is going to be a codimension 1 co-oriented foliation of M. And we ended last time with this theorem due to Cantwell and Conman, which told us that every oriented surface, so pretty boring if you're thinking compact, so including non-compact, is realized as the leaf of some C infinity F. So here highlighting the fact that we're thinking about compact manifolds, or again it would be kind of boring. So we want some way in which we can visualize objects in our manifold, realizing that our objects can get very, very complicated. And one approach to doing this, and pretty much what I'll be talking about, well, except for the last 5 minutes, is to think about using branched surfaces. So I talked a little bit yesterday about train tracks, and then Liam talked also about train tracks. So branched surfaces are the one-dimension higher analog of train tracks. So 1D higher analog of train tracks. And definition of branched surface due to Bob Williams, 1974, is that a branched surface is a space, and we can define things abstractly, but today we might as well think about, when we talk about branched surface, we're talking about C infinity embedded in a manifold. So C infinity embedded in M, just for convenience, sort of easier maybe to visualize. Locally modeled on one of the following. So I give you a point P, and I say, well, what does its neighborhood in this space look like? Well, most of my points are just surface points. So I could have a neighborhood that just looks like a plane. So in this case, P is just called a regular point. Or my P could have a neighborhood that looks like two surfaces coming together. So I've got that bottom surface drawn, I've got a second surface drawn, and it looks like train track, little piece of train track cross I. So I can think about this is an object, and my tangent plane field to this object is always defined. And in this case, P is called a double point. Or I could have three surfaces coming together. So I've got so I could think about taking this local model, and then I have a third surface that approaches from the bottom and then pinches in. So if I think I've got a train track here, I've got a train track here, and it's a way of combining those two things together. It's a single plane. Right. So we really are, in spite of what my drawing might be telling you, thinking about, so you can think about it as a spine, but I've given myself extra structure. So I've got a well-defined tangent plane, or tangent space. And we do want to allow today thinking about foliations in manifolds with non-empty boundary. So I just want to say that we also allow, let's maybe over here, codimension 1 co-oriented foliation. Today we're insisting that our boundary components be T2s, and we're insisting that each component, so each component of boundary M is either a leaf or it's transverse to F. So we want to allow ourselves boundary manifold points, and we want to allow ourselves boundary double points. So I guess I haven't drawn this consistently. Let's think about my manifold, this is my boundary of my M, and here's a point P, or I could have a point P like this. So again, this is still P, a regular point. This is a P, just a double point. This is telling me that B intersect boundary M is either a leaf of F, so if for each component C of boundary M, C not a leaf of F. Oh, I don't even have an F here. Ha ha ha. For each component C of M, C not equal to a component of B, B intersect C is equal to a train track or empty. And the train track could in fact just be a one manifold. And so I guess I should change orders. Here, this is P is called a triple point. These are the singular points. And we can think about the union of the double and triple points is called the branching locus of B. And B cut open along these points. So if I just think about restricting attention to the regular points, components are called branches of B. So I've got the branching locus, which is where interesting things are happening, and then I've got the complement of the branching locus. And just like we did with the train track, I can think about associating to my branch surface a regular neighborhood. So I can think about starting with B, associating to it a manifold, a regular neighborhood of B. I can think about being written as I-fibered in the sense that it can be written as a union of fibers. So just to sort of cheat and just look in this picture, I can think about So I can think about this cross I. And then if I was a better artist, I could draw my regular neighborhood around the triple point also. Let's see, what else do I want to say here? The other thing to notice is if you like the language of, well, first of all, the other thing to notice is that the boundary of this neighborhood B naturally decomposes as what we call the horizontal boundary and the vertical boundary. And the vertical boundary is just the boundary that is foliated by I fibers. So here's a little piece across I of my vertical boundary, and the horizontal boundary is the boundary that is transverse to the I fibering. So here is the part that's transverse to the I fibering, and these are the union of some I fibers. So if you're happy with the language of sutured manifolds, and you don't really have to be, you can think about n of b, boundary v, n of b, gives us a nice sutured manifold that I can associate to a branch surface. And also I can think about my b as sitting inside M, so I can think of M minus neighborhood of b, and again, boundary vertical neighborhood of b is equal to a sutured manifold. So we've got these objects that somehow we're going to relate back to foliations. I tried my best to think about avoiding using the word lamination, but I decided I couldn't succeed. So a lamination is a slight generalization of a union of minimal sets of a foliation. So a lamination is a foliation of a closed subset of your manifold. So you can think about it as being a generalization of union of minimal sets. So closed union, just to make sure I don't take sort of some limiting set of compact leaves. So in particular, any finite union of minimal sets is going to be an example of a lamination. You could think about the example we looked at where we had a genus 2 surface cross S1, and we thought about taking the suspension lamination and just filling in with stacked chairs. We could think about just the suspension lamination is an example of a lamination. So M equal to, say, take a closed surface and glue it by some monodromy, and let's say we pick our phi f to be hyperbolic, our phi to be pseudo-Anosov. So lambda, say, is a stable lamination of phi. Then lambda, which is just the suspension lamination of little lambda, unless I've got my lambdas and gammas mixed up, which is possible, is an example of a lamination.
Are those the regions that you blow up by? Like if I go a dimension down,
Okay.
torus, and I blow up along one of these blow-ups from last time, are those annuli? I get an annulus in the torus that's laminated.
Oh, okay, so you're saying, suppose I have a foliation by compact leaves and I do one of these blow-ups, so I have an annulus region, or if I have a non-compact leaf and I do a blow-up and I have, an all-cross-eye region.
What both are either of those laminated examples of lamination?
So if I have a foliation, that's a lamination. If I forget the leaves I added in the blow-up part, then what I have is a lamination. But also, I think of it also as a minimal set of the foliation. So yes, it is. Okay. And I guess just to notice right here, in general, there's no reason that this object right here is going to allow you to put stacked chairs in. Remember, we needed that infinite intersection number for that to work. So in particular, it doesn't necessarily extend to a foliation. And we've got a definition of what we mean by, and so I guess this is Gabay Hotel. So an essential lamination so we're thinking really generalization of Rabelais foliation. So is a lamination. Well, we want the lamination to satisfy some of the nice properties that Rabelais foliations do. So we want, for example, that leaves be pi1 injective. So lamination so that leaves are pi1 injective. We want to have no S2 leaves. And we want complementary regions to be irreducible. And then there's a slightly weird condition that we're not going to really worry about because everything we see is co-oriented today. So I have to be careful about what I mean by that. But basically if you're not filling up your whole manifold, there are weird ways in which you can hide compressing disks. But there are not very many weird ways. So as long as you rule out this, you win. Okay, so I talked last time about a train track carrying a geodesic lamination, and we now want to talk about laminations carried by bronze surfaces. So let me just go one dimension down. Suppose that I have my lamination just being this curve right here, so I can think about a slope 1 curve, and that's carried by, so this is my lamination, and it's carried by this train track. So I can think about just pinching along these are supposed to be disjoint copies of I. And you can see that I've got some, well, sorry, I haven't given you the definition. So lamination is carried by a bronze surface B if it can be isotoped to lie in this nice I-fibered neighborhood of my bronze surface so that the leaves are everywhere transverse to the I-fibers. So I talk about my slope 1/1 curve is carried by this train track because I can isotope it so it lies in this I-fibered neighborhood everywhere transverse to the I-fibers. And in general, 1 dimension higher, just a little bit more difficult to draw. My lamination is carried by a bronze surface if I can play this isotopy game. And you can notice an advantage that we're going to, looking ahead, this train track right here carries this slope 1 curve, but it also carries, any positive sloped curve. So next we want to think about, well, what does it mean for a foliation to be carried by a bronze surface? And there are 2 natural games you can play. And I'm going to focus on one. And I don't know if there's much point in giving exercises, but I'll leave the others in exercise. So definition. So, and actually, let's just have some notation first. So I can give you a, let's say, some foliation. And I can think about L as being a leaf of F. Or more generally, I can think about it as being a countable union of leaves of F. Countable union of leaves of F. And we saw last time that we have this operation called Danjois blow up. So I can take my F, I can Danjois blow up along L. We only talked yesterday about the case that my L was a single connected surface, but you can see all you really needed to take advantage of is that it intersected transversals countably often, which is satisfied by this. And let's just write D sub L F for the Danjois blow up of our original foliation along the leaf L. And then we say that a foliation is carried by a bronze surface if after some Danjois blow-up you can isotope the foliation, the leaves of the foliation, so that they lie in the nice N of B everywhere transverse to the I fibers. So definition, we say that a foliation is carried by B. If after possibly Danjois blow-up, well, I guess after Danjois blow-up, the leaves can be isotoped to lie in N of B everywhere transverse. And so an exercise, alternatively, you can give a definition that does not require Danjois blow-up. And you can ask yourself, why do Danjois blow up first?
A statement about all leaves simultaneously being isotoped into N of B, or
what, this one right here, or
no,
this?
the original definition.
Okay, so you do Danjois blow up, so that you can just isotope all the leaves. But sorry, I think I'm missing your point. So
No, you can't isolate all the leaves into NB, unless NB
I thought we were talking about the original. That's why you do the Danjois blow up.
you blow up and
You
then
blow up. Sorry.
Come
So
back to new
it's not Danjois blow up.
Right.
Sorry. Thank you.
Splitting.
Danjois splitting.
Yeah, okay.
Okay, so thank you. That's a really good point. Otherwise, nothing made sense. So if I have a leaf L D'Angevin blow-up says, you know, you end up with 2 copies of L. Remember, everything we're thinking about is co-oriented. So we blow up, we get 2 copies of L, and you know, you stick some foliation in here. D'Angevin splitting is to do this and not insert extra leaves. Thanks. So, right, so after D'Angevin splitting, the leaves can be isotoped to line NB everywhere transverse to the I fibers. And the other possibility is, I mean, so if we think, for example, about our irrational sloped guy, so we're thinking about that leaf is dense in my manifold. So this is e.g., this is irrational sloped leaf. Then I can think about splitting this leaf, and then it gets carried by, we've introduced this bygone, and now we can think about it as being carried by this train track. Or alternatively, I can think about, I've got this complementary region to my bronze surface, and you can give yourself conditions on how the leaves lie with respect to the region that's complementary to this N of B. So you do have choices, and one of those 2 choices is either you don't care or one is slightly better when it comes to making statements. Okay, so So suppose I'm interested in listing all foliations, all, let's say, taut foliations of my torus. I can notice that we saw what? We saw that any taut foliation, well, actually I guess we didn't see the complete story, but what's true is that any taut foliation of our torus is carried by one of 2 train tracks. So I'm not insisting on fully carried by, for anyone who knows the jargon. So we would like to know, is there some analogous statement when we're thinking about 3 manifolds? Is there some finite collection of bronze surfaces that carry every foliation? And we have some nice answers to this due to Gabai. And to simplify the statements, I'm going to now assume that M is atoroidal. So I'm going to be assuming that M is atoroidal, and I hope well, at some point
Is M still closed?
no.
Okay.
Um,
And does that,
So for today, M is if it's going to be compact. If it has boundary, the boundary is going to be some union of tori.
sure.
And we might have tori. Oh, I see. So you're making a statement. Okay.
No, but atorial should refer to the boundary, though.
Yeah, no, it doesn't. But I'm actually, you're probably making a good point. Maybe I want to be closed right now too, just to simplify my statements. In fact, yes, I do. So. I just have to say something more carefully if I have boundaries, so I can talk about that case also. But let me not risk it. So the first statement is the following. So suppose suppose you give me the 3-manifold and you also give me a triangulation of the 3-manifold. So the triangulation might be a simplicial triangulation, it might be a single vertex triangulation, it might be 0 efficient, it might be 1 efficient. I've got some triangulation of my manifold. And Gabay tells us that if I give you a co-oriented taut foliation, then there exists F prime a co-oriented taut foliation, so that the minimal sets, or the leaves of minimal sets of F prime lie in Hawken normal form. With respect to tau. And maybe let me just have a silly example off to the side where I have a torus, and to be able to do something interesting, I'm going to have to move away from being taut. But let's suppose that, so 1D lower. So let's suppose I have a torus, and let's suppose I triangulate it. And let's suppose my foliation looks like I've got, let's say this is a leaf, this is a leaf, and this is a leaf, and I've got ray annuli. Now, however much I work, I'm not going to be able to isotope my foliation so that the foliation lies in Hawken normal form with respect to my triangulation. What's true, though, is that if I swoop out the R leaves that are spiraling in on the circles, I can get the leaves of my minimal sets in Hawken normal form with respect to tau. So how many people here know what I mean when I say Hawken normal form? Oh, okay, great, thanks. Then I'd better say something. Okay, so I have a triangulation of my manifold. And let me white sheet. Okay, so I have my manifold written as a union of tetrahedra, and I would like surfaces to meet my tetrahedra in particularly nice ways. So in particular, I get very, very unhappy if I see a 2-cell where I have non-minimal intersection of my leaf with my 1-cell. But thinking 1 dimension up, I would like my leaves to meet my tetrahedron in unions of very nice little surfaces. So I'm completely happy if I look at a component of a leaf and intersected with a tetrahedron, and I see a triangular leaf of this type. So this type means it separates off a single vertex. It crosses all the 1 cells minimally, and it cuts off, and I see I have 4 of them because each one cuts off a vertex. So this picture is not meant that I want every surface to intersect in unions of these, just that anything that looks like this is good. I'm in Hawken normal form. And then I could instead think about, choices of quadrilateral that separate off opposite pairs of opposite edges. And let me just draw one of these. So I say that a surface, so given my manifold together with the triangulation, we say that the surface is in Hawken normal form. if for every leaf L of, given surface, sorry, is in Hawken normal form, so surface S is in Hawken normal form if for every tetrahedron let's say delta of tau, S each component of S intersection delta has one of the forms either a quadrilateral or a triangle. So one dimension lower, this is a non-example, this is bad, but something's in Hawken normal form if it lies minimally with respect to the one skeleton of my triangulation of my surface. So 1D lower, I'm not in Hawken normal form here, I'm in Hawken normal form, but in terms of surfaces, a surface is in Hawken normal form if it meets each tetrahedron in components that have to have one of these two forms, either a quadrilateral that separates off two opposite edges or a triangular region that separates off a vertex. And then my leaves of my foliation or my lamination are in Hawken normal form if for each leaf I have this condition satisfied. And when I'm thinking about foliations, I'm really actually able to thinking about them as being embedded in R3 with some associated height function. And so then I'm thinking about, I've got some Morse function where I'm really thinking about leaves looking like this. So I don't really care if and so then I can see that my leaves are going to intersect. I'm going to see two different types of triangular region, and I've got my quadrilateral in between, the quadrilaterals in between the two vertices that are medium height. So in general, if I think about a surface, I can have all these various possibilities. In general, when I'm thinking about Hawken normal form for foliations, really this is the picture. I can always wiggle my triangulation around so that I have the vertices locally lying at distinct heights.
In this theorem of Gabay here,
Okay.
F prime has nothing to do with F, right? Like it's just, if you start with a taut foliation, you can produce a good taut foliation.
No, he gives a bit, so actually originally Mark Brittenham sort of set up this game of replacing F by F prime by sort of laminations instead that are somehow related to the original F. But Gabay did a careful analysis, so you can explicitly describe the ways in which the F and the F prime can differ.
Sure, but I mean, like in the statement here and like in the way we're going to use it, we don't need a relationship?
Yeah, we don't need to know. So really underlying the whole, whatever I can fit in talking about today, is the L-space conjecture. So thinking about, we just care about existence of a coordinated taut foliation. We don't care about describing all of them. Right. Okay, so one is that if I fix a tau, then, it might be that I have to do something a little bit odd, but it's not too odd. And we have something that does lie in Hawken normal form with respect to the triangulation. And this is very nice because there's a standard game. If I know that there's a standard game, for example, when you're trying to say that there are finitely many incompressible surfaces up to isotopy. You can put your surfaces in Hawken normal form. You can see that there are finitely many non-product complementary regions, and you can do a count. If you're thinking about branch surfaces and you've got a whole bunch of leaves intersecting in these sort of nice embedded quads and triangles, triangular regions, you've got the same sort of game you can play. You can say, oh, okay, if I've just got a product region, I can pinch my disks together. And I see that as I start pinching, I start getting these branch surfaces. I step back and I say, oh, okay, again, the same thing that gave me a finite number of non-isotopic incompressible surfaces gives me a finite number of branch surfaces. I step back a little further and I say, oh, but these bronze surfaces are absolutely hideous. Bronze surfaces are not good for me unless they satisfy some other properties. And then you say, okay, phew. You know, Gabai showed that you can split, and there's sort of a standard way in which you can split so that your bronze surfaces are nice. So this is telling you that there exist finitely many, and I'm going to use essential, but I don't want to take the time to define it. So think nice bronze surfaces. That carry all, well, we have problems with tori, which is why we ruled this out, but all taut foliations. So really that's a nice clean statement about rabless. And today we care about taut. Another thing that Gabai proved is that you can do better in the following sense, that there's some tau naught triangulation of M such that every taut foliation can be isotoped to lie in Hawken normal form with respect to tau naught. So if we go over to this dumb example over here, I can say, oh, okay, well, I could always refine my triangulation so that this foliation, without doing any changes, is going to be transverse to it's going to be in Hawken normal form with respect to my triangulation. And then you would say, oh, okay, but, you know, I'll give you 100 ray annuli and you run into treble. Yes, this is a bad example. When we move up a dimension, you can think about those circles as corresponding to tori, and you have to give a more careful statement in that case. But so what this is saying is that there's some triangulation for M so that every co-oriented taut foliation lies in nice position, lies in Hawken normal form with respect to that triangulation, where Hawken normal forms means this picture right here locally. Okay. Okay, so there are nice bronze surfaces and there are super nice bronze surfaces. So Gabai Ortel introduced this notion of incompressible bronze surface. So if, let me just say it in this way, so if F is a foliation carried by an incompressible bronze surface, then you know that F is taut. Tao Li introduced the notion of laminar bronze surface. And I won't give you the definition. It's a bronze surface that's nice. And the issue with incompressible bronze surface is, well, if it carries a foliation, you know the foliation is nice, but you don't know that the bronze surface actually carries one. So if you're looking for something, you can't make any conclusions. Tao Li, his result is that if you can find a laminar bronze surface, you know that there's an essential lamination. So if you can find a laminar bronze surface which has nice enough complementary regions, you know that you have a taut foliation. So if you can find a laminar bronze surface with nice enough complementary regions, then you know that there's a taut foliation. And Ian Agel and Tao Li took advantage of these laminar bronze surfaces and the fact that there are finitely many essential bronze surfaces to say, hey, there's an algorithm to decide whether or not a three-manifold contains a rabless foliation, or if you're atoroidal, a taut foliation. So theorem due to Agel and Lee there's an algorithm to determine whether M contains a CTF. So again, we're assuming atoroidal. There's a statement in the toroidal case, but let's skip that for now. So there's an algorithm to determine whether M contains a co-oriented taut foliation, and basically a sketch is, by Gabai we know that there's a finite set of essential ground surfaces which carry all, really carry all essential laminations, and then you have to worry about complementary regions. And then you can split in two ways. So there exists an algorithmic splitting technique that stops if B doesn't carry. And there exists an algorithmic splitting technique that stops if BI does carry. You have no idea how long it's going to take, and it's the sort of thing that doesn't naturally lend itself to an implementation. The other thing that's really, really nice about Tauli's result, if you're interested in beginning with a manifold with non-empty boundary, and first looking at branch surfaces that meet the boundary of your M in a train track.
Sorry, it's Gabai's result actually tells you explicitly how to construct the BI.
Well,
Is there just an algorithm if I hand you the BI, or do you have to
well, first of all, I've been a little sloppy in this statement right here, which I was hoping to sneak by everyone. It was actually purposely done. But really what you're finding is that you've got a minimal number of branch surfaces that are going to carry sort of minimal sets of foliations. And then you can start looking at the complementary regions and seeing if those are taut sutured manifolds. But the game is, yes, you give me a triangulation, and you've got the same sort of Hawk and normal. Oh, yeah. So the same sort of argument that works for surfaces. So you know that any essential surface is carried by one of finitely many branch surfaces, and it's algorithmic, yes. So the same sort of game works. Okay, this is a really, really nice result. So if you've got a manifold with non-empty boundary, then you know that you can find co-oriented taut foliations. For example, you could use Gabai, and sutured manifold hierarchies. And if you've got boundary non-empty, you can look at the branch surface and you can see whether it strongly realizes any slopes. And if the branch surface is laminar, Tauli tells you that if you strongly realize slopes, then you can extend the lamination carried by your train track into a lamination on the three manifold. So if you can find a laminar branch surface with a train track so that the train track realizes some family of slopes, say, you know that there's, for each slope in that family, there's going to be an essential lamination that realizes that slope. If you're interested in weakly realizing, I think it's still true you've got a limit of his game, but I would have to think about it a little more carefully. Originally, we were just mostly caring about strongly realize. But it's probably true for weakly realize also. So if you have a branch surface that's laminar, it has a train track, any slope that's carried by the train track is realized by some co-oriented taut, well, some essential lamination in the complement. And if the complementary regions are nice enough, you know you have a co-oriented taut foliation. So that's really useful. I realized as I was preparing this talk that it's almost impossible to really say anything. So here were the basic definitions of bronze surfaces. I now just want to list the various ways that I know of trying to find a co-oriented taut foliation. And I can be a wimp and use the excuse that, well, I changed the way I was writing my talk, so I was writing this list at 1 o'clock in the morning, and therefore might have inadvertently left someone out. So if I have done, and in particular if it's anyone in this room, but more generally, do let me know so that I can make sure this is something I know about. So what I want to do here is just sort of ways of constructing CTFs. And sorry, here I'm not even going to try to say more than throw out some words, and I'm running off immediately after this talk, but I'm happy to answer any emails. So there's GABI, and so if we're irreducible and not a rational homology sphere, we know that we have a taut sutured manifold hierarchy and this leads to, I want to think about it in terms of the finite depth bronze surface construction sort of going forward, but of course we could do the going backwards. And so this gives us CTFs. You can think about sort of there's sort of weak generalizations of these, or we can wiggle these somehow. And then there's a bunch of sort of ways in which you can modify these, but still, again, using taut sutured manifold hierarchies. There's work of Kal-El-Carr, or there's work of Lee, Dasbosh. There's work So this I want to think about as anything that falls under the description, there is a taut sutured manifold hierarchy. You could, in general, think about using a hierarchy, but it's not a taut sutured, but not taut. And there's recent work of myself and Charles Delman where we do this. And I have to say that this recent work was inspired by the L-space conjecture, because in particular, all Montesinos and all alternating L-space knots were completely known. And we went and looked, and any manifold obtained by surgery on either an alternating knot or a Montesinos knot is going to satisfy the L-space conjecture. We don't know, how to what extent we can generalize these games. But again, GAVI, you can think about, you had a finite depth branch surface. Here we're using hierarchies to get finite depth spines, but then the branch surfaces we get are not usually finite depth. There are results that take advantage of tangle decompositions. So Delman and Wu. There are constructions that are sort of just, let me just say ad hoc. That's sort of an insult though. There are constructions due to Brittenham and Otel. Basically, there's this type of branch surface you can find, and then you can say, well, it lives somewhere, but it's hard to tell, given a particular example, whether it contains one of these things. So these we could use, well, what do we have here? We've got this notion of an algorithm that tells us whether we have a CTF. So we can think about using triangulations. So triangulations. And in particular, Gabay has a result in which he says the existence of a CTF is equivalent to the existence of a combinatorial volume preserving flow. So that's a triangulation with a weight on the one skeleton that satisfies some very natural correspondence between taut foliations. So we can think about combinatorial volume preserving flow. It also gives some topological analog to that Sullivan notion of geometrically taut. And then Dunfield, Nathan Dunfield, has triangulations satisfying actually a fairly similar condition to Gabay's, which he can use in his program very effectively. So these are really nice in the sense that, they're beginning to look a little more general. Maybe they're too general because what are you using? But those are very, very nice. There's work of Colan and Fermo, where you can think about trying to play the reverse game to Eliashberg-Thurston. If you have a pair of context structures, one positive and one negative, and they're nice enough, then sometimes you can find yourself, so let me just write nice, and let's write sometimes. Also a very nice paper, which I recommend strongly. And then there are sort of results where, maybe you can find, really the only place I know about these are, you've got knot complements which have simple enough structures. So maybe you've got, so the two cases are two-bridge knots, knot complements generally. We can think about knots that are fibered with genus 1. So we can think about, we've got some Morse function either to an interval or to S1 where the regular levels, where the minimal genus Seifert surface meets the levels in something very simple. So either you have two-bridge, and so at most levels you see S2 minus 4 punctures, or you have T2 minus D2 0. And then this is simple enough that you can analyze the possibilities. And Hatcher, Rami Naimi, and Charles Delman have work which does this. Okay, so these are the ways that I know of, and I'll stop here. Thank you very much. I was going to run to the train station with my